Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to our next lecture. Today we are going to look at another technique for the feature reduction of our data that is known as the feature embedding. Basically, feature embedding is a technique that translates high dimensional data to lower dimensional data. How that is done, we look at that, but before that we look at some linear algebra which is required to understand this concept, this algorithm. Let us say that we have a matrix A which is a symmetric matrix, then it would only be symmetric if it is equal to its own transpose. So, if a matrix is equal to its own transpose, it is a symmetric matrix. Then there is concept number 2, which is diagonalization of a real symmetric matrix, which is also known as the spectral decomposition, right? And then there is a third point, which is that A is a square matrix of rank D cross D, which is real and symmetric matrix. Then its D dimensions would be linearly independent eigenvectors if the eigenvalues are real and the eigenvectors are real and orthonormal, perpendicular to each other. If they fulfill these two conditions, then they would be linearly independent. A can be decomposed as WD WT, where W is a eigenvector matrix and D is an eigenvalue matrix. So, you must know that we can convert it something like this, which could be easily decomposed, right, and we will also see it. With this lecture, I will provide you some Python code for your experimentation, and you will have to understand all the concepts which are discussed in this presentation using that code. Now, we look at the feature embedding. Let X is the n cross D matrix. For example, we have if we work with the iris flower data set, so we have this 140 into 4 matrix data set, which is there are 140 examples and there are 4 features for each example, where n is the number of the instances and D is the input dimensionality. Let the covariance matrix of X is also a D dimension. We have already studied that if there are D dimensions in our data, then the covariance matrix would be a D by D, D cross D. And if X is centered to have a 0 mean, it is equal to this covariance matrix would become equal to this matrix, right, where X transpose is X. So, why is this and what is this? Let us see that. We have this covariance matrix, and the first entry that would be sigma 1 1, and it would be of course square. If it is square, that could only be obtained with the help of this expression X transpose X when it is multiplied. Go back and look at the lecture of PCA where we discussed that what is this. Previously, we may have explained this term over there, right. So, in that way, the covariance matrix would take the form of this kind of stuff. For example, this is 2 2, right, it is square, it is 0, and here we have it is 0, and here 0, and here we have 3 3 square. So, I hope this is very easy to understand for you people, that how this is generated and how this term has come up, right. So, this term is very much associated with covariance matrix, and if covariance matrix takes a special form, then we can represent it with the help of this expression. Okay. PCA uses the eigenvectors of xt x. Remember, this xt x is now basically this our covariance matrix, and we find the eigenvalues and the eigenvectors of this covariance matrix. The spectral decomposition of this covariance matrix could also be given with the help of this expression, where W represents the eigenvectors and D represents the eigenvalues, right. And by multiplying in this way, taking a dot product in this way, it would generate back the original covariance matrix, where W is D cross D and it contains the eigenvectors, and D is a D cross D diagonal matrix which contains the corresponding eigenvalues. Let the eigenvectors are sorted according to their eigenvalues. If we have sorted the eigenvector matrix according to their eigenvalues in descending order, where the first column, if this is eigenvector matrix, the first column correspond to the highest eigenvalue, second column correspond to the second highest eigenvalue, third column correspond to the third highest eigenvalue, and so on. In that way, the first column of our matrix of W would contains the first PCA, principal component analysis, principal component, which is the highest one. Then there is second highest and third highest and so on. If XTX has rank k less than D, for example, if we make our covariance matrix in such a way that it has small number of dimensions as compared to D, then all DIIs for I greater than k would be 0, which would be beyond k. For example, if we take the case of 4D data, and this is the covariance matrix represented with help of this expression, right, and we reduce it to some smaller dimension. For example, the smaller dimension is 3, which is shown with the shaded orange shaded area. Here you can see that all these, this is sigma 1 1, right. Next would be next variance, which is sigma 2 2. Here it is sigma 3 3, right. And this statement says that all other sigmas, for example this, would be 0 because they are beyond x and we are not including them in our computation. So I hope these two lines are very much clear to you people on this slide now. The feature embedding mechanism, it maps the new k dimensional space by taking a dot product of the original inputs with the eigenvectors, right. It means that it finds the eigenvectors and takes the dot products with the original input, and by doing this, right, these are the eigenvectors and this is the original input. When they are, the dot product of these two values is taken, they give us new points, new values, which are Zi. Given that this is an eigenvalue and this is the eigenvector for some feature I, are the eigenvalues and eigenvectors of this, then we can write it like this. Previously we have written it like this in our previous discussion: sigma Wi, that is equal to this I Wi. That was our previous expression, but now we have replaced this sigma, the covariance matrix, with this x transpose x. Pre-multiplying x, now we multiply the left hand side and the right hand side with x. We find that when x is multiplied with xt and we have taken it as a bracket, and here we have placed x and Wi, this, how can we do this? Because we have assumed that the matrix is symmetric, and a symmetric matrix has the same transpose equal to itself. In this particular shape, now this has been formed over here. If we consider that this is the eigenvector matrix, this is the eigenvector matrix, this, you can say that this is A W equal to lambda W, which is the basic equation for the eigenvalues and the eigenvectors, which we have seen in the previous lecture. So here we can consider it as A x into x transpose, as A x into Wi as feature as eigenvector, right. The multiplication, the dot product of these two would provide us the eigenvectors. This must be the eigenvectors of xxt with the same eigenvalues. Note that xtx is d into d dimension, whereas xxt is into n dimension. How is that? This point is clear with the help of these equations. X is n cross d and x transpose, it would be d cross n. Then when we take x into x transpose, it means that n into d, then d into n, so it would be n into n. However, x transpose x is equal to d into d, because we get this first, this later on, and these two dimensions would remain and inner dimension would be crossed out. So, we will get a d cross d dimension vector. Its spectral decomposition, if we perform the spectral decomposition of this covariance matrix, which is diagonalized, it gives us this result, which is VEVT, where V is the n cross n matrix containing the eigenvectors of x transpose in the columns, and E is again n cross n matrix which contains the corresponding eigenvalues. The k n cross n dimensional eigenvectors of x(t), if we have reduced x(t) to k dimensions, right? And we have seen in the previous PCA that how we reduce them. We filter out some of the eigenvectors and we keep some of the eigenvectors. Then this is a very important point to understand, right? We try to look at here again. The k n dimensional eigenvectors of this matrix, which is a covariance matrix, are the coordinates in the new feature embedding space and is known as feature embedding. What does that mean? It means that this will provide us the values that could be mapped, that are mapped into k dimension space. This n dimension, right, we just can remove this n dimension coordinates, provide us the way to map the value in the lower dimension space. Let me explain this feature with the help of this figure. Here you can see that we have this point in 3 dimension, right, and it is represented with the help of 3 coordinates. If we have to project it on 2 dimension, it would be somewhere here, right, and now this point could be represented with the help of 2 coordinates x and y instead of 3. So, this gives us new coordinates for this point in lower dimension space. So, the concept is clear. I hope. If it is not, then look at the things that I have said in this slide again. Eigenvectors are usually normalized to have unit length. So, if the eigenvectors of x transpose are Vi, this is the covariance matrix. If its eigenvectors are represented by Vi, then Vi is equal to xwi this. What does that mean? It means that x transpose x is our covariance matrix and x transpose is another matrix which is derived from the same one, right, and they are actually equal through some operation. So, this would have the eigenvalues represented by lambda I, and it would have the eigenvalues represented as Vi. Eigenvalue vectors are usually normalized to have unit length. So, if the eigenvectors of this are this, then we can say that the eigenvalues of the newly transformed or translated matrix are actually normalized by the eigenvalues of older covariance matrix, right. Sum of squares of xwi is this, right. So, if we have Vi column I of V, right, calculated, and we want to get xwi, we multiply with the square root of eigenvalue. How? Here you can see that we use this expression, right. This is the square root of eigenvalue previously we have seen in this slide that E represents so here we have seen that the spectral decomposition, this is represented as this, right. Again, look at that, how we have changed from this to this, right. So this is the trick over here, and then if we have changed it into this form, then we can decompose this into this VET, where V is the new eigenvector and eigenvector set or matrix, and E is the new eigenvalue matrix. So here, if we have Vi, we know about Vi calculated, and we want to get this xwi back, which is represented by Z. Remember that here we have represented Z as that is equal to Wix. So we want to get Wix or XW back, right. We will do this expression, which is we will multiply with the eigenvalues, right, square root of eigenvalue to get this back. And just this is given for your understanding. These are the eigenvalues of the translated matrix, and these are the eigenvalues of older. We will not use lambda, however, I have written this expression for your own understanding. If D, the dimension of data, is less than n, it is simpler to work with this. We will use PCA. However, if D, the number of dimensions, is greater than the number of samples, and then it is easier to work with X transpose. So these 2 points you must remember, that if the number of dimension is less than the number of samples, we would be working with this, mean we will be using the PCA. In other case, if the number of dimension is greater and the number of sample is smaller, then we will be working with this, right, and in this case we will be applying these formulas to find out the values. Let me take the example. There are 40 images of facial recognition, and let rank of the matrix in number of eigenvectors having associated eigenvalues is greater than 0. Although let us say that each image has this much dimension, 65,536. So the covariance matrix would be again of the size D, XD, which is this much higher. The rank can never exceed 40, right, because we will have this for the first image, we will have this for the second image, and up to 40 we will reach. Rest of the things would be discarded, as we have seen in the previous slide. Contrary to PCA, we do not learn a projection model but get the coordinates directly in the new dimension space. If we have new test data, we should add them to X and redo the calculation again. The element Ij of this, the new covariance matrix, is equal to the dot product of instances I and j, that is Xi transpose Xj, right, and actually this is given as Xi and j would be equal. If dot product is similarity measure, if we use dot product as a similarity measure between the two vectors, then X transpose is n cross n matrix of pairwise similarities. How pairwise similarities? Because it is giving the similarity between Xi and Xj. So feature embedding is a method of placing instances in a k-dimensional space such that pairwise similarities in the new space respect the original pairwise similarities, right. Whatever the similarity between the two pairs was there in the original space, in new space the similarity would be same, there would be no difference. I hope the concepts are clear to you. See you next time in next lecture. Allah Hafiz.